name is Pat Murphy and I'm a part of Team Zebo. Our brief was to design an earth berm to protect Thomond Village from flooding. The berm will be constructed in the area right there behind me, and this design must ensure the berm retains water without significant seepage loss or failure.
The key to us succeeding in our projects is to keep the soil mechanics triangle in balance.
The first step in the soil mechanics triangle is the ground profile. This was done by carrying out a site investigation by digging trial holes. The main aims of this was to check the various stratas of soil, check the depth of the water table, and to collect soil in which we will test in the lab.
In order to classify our soil, we use the acronym MCCSSOOW. This acronym consists of moisture content, colour, consistency, strength, structure, organic and non-organic matter, other features, and the water table. While on site, we found our topsoil had a depth of 0.46 metres, while our dark soil had a depth of 0.59 metres. Our brown soil had a depth of 0.78 metres, and our clay pink soil had a depth of 2 metres. We got this trial log from our friends in civil engineering, and as you can see, the two trial logs are very similar, although this trial log was taken 50 metres away.
Our research has shown us that clay is the most suitable type of soil to be used in the construction of our earth berm, as it is easily compacted and impermeable. This is because the particle size of clay are a lot smaller than any other type of soil.
The second step in our soil mechanics triangle is soil behaviour. We established this by doing lab tests. These lab tests identified the properties and characteristics of the soil we were taking from the borrow site. The tests we completed were cone penetration, sieve analysis, CBR, Proctor, permeability and plasticity.
We did a cone penetration test in order to find the liquid limit of the soil. To do this, we mixed a sample of the soil into a paste at different moisture contents. We repeated this test a number of times, each time increasing the moisture content of the soil until it gave us a penetration of 20 millimeters. Once we plotted the graph, we were then able to get the liquid limit of our soil, which is 53%. Once we had our liquid limit, we then moved on to our plastic limit test, as shown here in the video. The plastic limit shows the water content at which the soil ceases to be plastic and becomes a semi-plastic solid.
We determined our plastic limit to be 28.4%. We then took this from our liquid limit, which is 53%, to give us our plasticity index of 24.6%.
The reason we did all this was so we can now look at Casagrand's chart to classify our soil. We were able to classify our soil as a clay with high plasticity. We did a Proctor test in order to find the relationship between the optimum moisture content and the maximum dry density of the soil. By using our results, we found the maximum dry density to be 1.5 grams per metre cubed and the optimum moisture content to be 24%. By getting these results, we were able to specify the compaction to be done on our berm. We carried out a CBR test to obtain the soil's bearing capacity. This process is similar to that of the Proctor test, except a larger hammer is used and the number of blows increased. We then put it into the CBR testing machine, which resulted in an indentation. We measured the penetration of this indentation and in proportion to the force causing this penetration. We did this test to find out the strength of our soil. Our CBR result was less than 3%, which meant that our soil is not strong enough to support the plant machinery that we hope to compact it with. However, by decreasing our moisture content, we were able to increase our CBR, so therefore our soil is suitable. We did a sieve analysis to determine the soil's particle size distribution. This told us the percentage clay, silt and sand that were in our sample, and we were able to grade our soil. However, our results were inconclusive as the clay sample was not crushed out enough to pass through the 0.063mm sieve. So instead, we used a value for clay that we got from Craig's Soil Mechanics. We did a falling head test to get the permeability of the soil. We got our results and we will use this later to help us calculate the seepage. This tells us how much water will flow through our berm.
The third and final stage of our soil mechanics triangle is appropriate model. However, we must first look at failure modes of earth berms and also solutions to these problems. These problems can be categorised in three groups: hydraulic failure, seepage failure and structural failure.
Seepage always occurs in dams. If the magnitude is within the fan limits, this may not harm the stability of the dam. However, if seepage is concentrated and uncontrolled beyond limits, this may lead to failure of the dam. By drawing a flow net of our berm and using the permeability value we got from our lab test, we were able to determine the seepage rate through a berm by using this formula. Seepage occurs through an This causes boiling.
Using the formula as shown, we were able to calculate our seepage rate as shown here.
Boiling occurs when the exit water pressure is greater than the resistance of the soil. This causes the soil particles to begin to wash away. Piping is caused by continuous boiling. The hole here deepens as more and more material is taken away. As a result, the burn will sink or settle, leading to ultimate failure.
A filter is put in place so piping will not occur. The filter draws whatever seepage is in the burn and extracts it safely. The reason the filter is here is because boiling is at its greatest here. This is because there is a high pressure acting up and a very low pressure acting down. Seepage lines through a burn would now look something like this.
The most common type of structural failure is slope collapse. This happens when the slope of the berm is too steep and causes instability.
To tackle overtopping, we will have a free water allowance of 1 metre. This means that the water will only come within 1 metre of the crest.
Hydraulic failure is overtopping and erosion. Earth embankments are not designed to be overtopped and are therefore particularly susceptible to erosion. Once erosion has begun, it is almost impossible to stop.
From our research of previous burn designs, our burn will have a slope of 3:1 on the upstream side and a slope of 2:1 on the downstream slope. This will prevent any instabilities in our burn. A flatter upstream slope required by all earth burns allows the saturated section below the water level to resist erosion on the face of the embankment.
Along with the potential problems we found and the solutions we discovered, there are also other features that must be incorporated into our burn design, such as a cut-off trench. Cut-off trenches are integral to berm design. They serve two main purposes. One, the cut-off trench locks down the berm into the surrounding soil and prevents the berm from sliding. The second point is that the cut-off point helps prevent seepage by extending the flow lines. The flow lines will be extended as shown.
One of the points raised in our brief was the possibility of swelling soils, and would this affect the integrity of our burn? We discovered that yes, the soil we are using is susceptible to swelling. We know this from looking at our table here. We previously found our plasticity index to be 24.6%, therefore our soil is an expansive soil. Swelling occurs when swelling pressure is greater than the effective stress in the body of the soil. Moisture content plays a major role in the swelling and shrinkage of the soil. When water molecules are added to the soil, the water molecules are absorbed between the soil plates. This increases the gap between the soil plates, increasing the soil pore water pressure. This causes heave in the dam.
Our construction process is shown here.
Health and safety plays a big role in every aspect of construction, and our burn is no different. On all construction sites on which transport vehicles, earth moving or material handling are used, the project supervisor for the construction stage shall ensure that safe and suitable access ways are provided for them. Transport and pedestrian routes are also organised and controlled. The berm should be inspected frequently for structural fails. Clear and visual signs at all access points. Life buoys should be provided around the structure and regularly checked. Fencing is vital to keep people, livestock and vehicles off sensitive areas such as the spillway, the outfall and the embankment. Good fencing will assist in maintaining the grassland, will prevent erosion and will stop the control access to the dam and reservoir area. Trees like this one here behind me do not help to stabilise the soil, and their roots will eventually reach the water. That is why we don't put any trees near the embankment.